The Moon is Earth's only natural satellite. It orbits Earth at an average distance of 38,43999 km, 238,854 meters, about 30 times Earth's diameter. The Moon's orbital period, lunar month, and rotation period, lunar day, are synchronized by Earth's gravitational pull at 29.5 Earth days, making the same side of the Moon always face Earth. The Moon's pull on Earth is the main driver of Earth's tides. In geophysical terms, the Moon is a planetary mass object or satellite planet. Its mass is 1.2% that of the Earth, and its diameter is 3,474 km to 159 meters, roughly 1/4 of Earth's, about as wide as the contiguous United States. Within the solar system, it is the largest and most massive satellite in relation to its parent planet, the 5th largest and 5th most massive moon overall, and larger and more massive than all known dwarf planets. Its surface gravity is about 1/6 of Earth's, about half that of Mars, and the second highest among all moons in the solar system, after Jupiter's moon Io. The body of the Moon is differentiated and terrestrial, with no significant hydrosphere, atmosphere, or magnetic field. The lunar surface is covered in lunar dust and marked by mountains, impact craters, their ejecta, ray-like streaks, rills, and, mostly on the near side of the Moon, by dark maria, seas, which are plains of cooled lava. These maria were formed when molten lava flowed into ancient impact basins. The Moon formed 4.51 billion years ago, not long after Earth's formation, out of the debris from a giant impact between Earth and a hypothesized Mars-sized body called Theia. The Moon is, except when passing through Earth's shadow during a lunar eclipse, always illuminated by the sun. But from Earth, the visible illumination shifts during its orbit, producing the lunar phases. The Moon is the brightest celestial object in Earth's night sky. This is mainly due to its large angular diameter, while the reflectance of the lunar surface is comparable to that of asphalt. The apparent size is nearly the same as that of the Sun, allowing it to cover the Sun completely during a total solar eclipse. From Earth, about 59% of the lunar surface is visible due to cyclical shifts in perspective, libration, making parts of the far side of the Moon visible. The Moon has been an important source of inspiration and knowledge for humans, having been crucial to cosmography, mythology, religion, art, timekeeping, natural science, and spaceflight. The first human-made objects to fly to an extraterrestrial body were sent to the Moon, starting in 1959 with the flyby of the Soviet Union's Luna 1 and the intentional impact of Luna 2. In 1966, the first soft landing, by Luna 9, and orbital insertion, by Luna 10, followed. On July 20th, 1969, humans for the first time stepped on an extraterrestrial body, landing on the Moon at Mare Tranquillitatis with the lander Eagle of the United States Apollo 11 mission. 5 more crews were sent between then and 1972, each with 2 men landing on the surface. The longest stay was 75 hours by the Apollo 17 crew. Since then, exploration of the Moon has continued robotically, and crewed missions are being planned to return beginning in the late 2020s. The English proper name for Earth's natural satellite is typically written as Moon, with a capital M. The noun moon is derived from Old English mona, which stems from Proto-Germanic menon, which in turn comes from Proto-Indo-European mensis month, from earlier menat genitive meneses, which may be related to the verb measure, of time. Occasionally, the name Luna, Lu, is used in scientific writing and especially in science fiction to distinguish the Earth's moon from others, while in poetry, Luna has been used to denote personification of the Moon. Cynthia, Cynthi, is a rare poetic name for the Moon personified as a goddess, while Selene, Seli, Ni, literally moon, is the Greek goddess of the Moon. The English adjective pertaining to the Moon is lunar, derived from the Latin word for the moon, luna. Selenian. Casalenian is an adjective used to describe the Moon as a world rather than as a celestial object, but its use is rare. It is derived from Selene Selene, the Greek word for the Moon, and its cognate Selenic was originally a rare synonym, but now nearly always refers to the chemical element selenium. The element name selenium and the prefix seleno, as in selenography, the study of the physical features of the moon, come from this Greek word. Artemis, the Greek goddess of the wilderness and the hunt, also came to be identified with Selene and was sometimes called Cynthia after her birthplace on Mount Cynthus. Her Roman equivalent is Diana. The names Luna, Cynthia, and Selene are reflected in technical terms for lunar orbits such as apollune, pericynthion, and selenocentric. The astronomical symbols for the moon are the crescent and decrescent. For example, in lunar mass. Isotope dating of lunar samples suggests the moon formed around 50 million years after the origin of the solar system. Historically, several formation mechanisms have been proposed, but none satisfactorily explain the features of the Earth-Moon system. A fission of the moon from Earth's crust through centrifugal force would require too great an initial rotation rate of Earth. Gravitational capture of a pre-formed moon depends on an unfeasibly extended atmosphere of Earth to dissipate the energy of the passing moon. A co-formation of Earth and the moon together in the primordial accretion disk does not explain the depletion of metals in the moon. None of these hypotheses can account for the high angular momentum of the Earth-Moon system. The prevailing theory is that the Earth-Moon system formed after a giant impact of a Mars-sized body named Theia with the proto-Earth. The oblique impact blasted material into orbit about the Earth, and the material accreted and formed the Moon just beyond the Earth's Roche limit of dietary 2.56 R. Giant impacts are thought to have been common in the early solar system. Computer simulations of giant impacts have produced results that are consistent with the mass of the lunar core and the angular momentum of the Earth-Moon system. These simulations show that most of the Moon derived from the impactor, rather than the proto-Earth. However, models from 2007 and later suggest a larger fraction of the Moon derived from the proto-Earth. Other bodies of the inner solar system, such as Mars and Vesta, have, according to meteorites from them, very different oxygen and tungsten isotopic compositions compared to Earth. However, Earth and the Moon have nearly identical isotopic compositions. The isotopic equalization of the Earth-Moon system might be explained by the post-impact mixing of the vaporized material that formed the two. Although this is debated, the impact would have released enough energy to liquefy both the ejecta and the Earth's crust, forming a magma ocean. The liquefied ejecta could have then reaccreted into the Earth-Moon system. The newly formed Moon would have had its own magma ocean. Its depth is estimated from about 500 kilometers, 300 miles, to 1,737 kilometers, 179 miles. While the giant impact theory explains many lines of evidence, some questions are still unresolved, most of which involve the Moon's composition. Models that have the Moon acquiring a significant amount of the proto-Earth are more difficult to reconcile with geochemical data for the isotopes of zirconium, oxygen, silicon, and other elements. A study published in 2022, using high-resolution simulations, up to 108 particles, found that giant impacts can immediately place a satellite with similar mass and iron content to the Moon into orbit far outside Earth's Roche limit. Even satellites that initially pass within the Roche limit can reliably and predictably survive by being partially stripped and then torqued onto wider, stable orbits. On November 1, 2023, scientists reported that, according to computer simulations, remnants of Theia could still be present inside the Earth. The newly formed Moon settled into a much closer Earth orbit than it has today. Each body therefore appeared much larger in the sky of the other. Eclipses were more frequent, and tidal effects were stronger. Due to tidal acceleration, the Moon's orbit around Earth has become significantly larger, with a longer period. Following formation, the Moon has cooled and most of its atmosphere has been stripped. The lunar surface has since been shaped by large impact events and many small ones, forming a landscape featuring craters of all ages. The Moon was volcanically active until 1.2 billion years ago, which laid down the prominent lunar Maria. Most of the mare basalts erupted during the Imbrian period, 3.7 billion years ago, though some are as young as 1.2 billion years and some as old as 4.2 billion years. There are differing explanations for the eruption of mare basalts, particularly their uneven occurrence, which mainly appear on the near side. Causes of the distribution of the lunar highlands on the far side are also not well understood. Topological measurements show the near side crust is thinner than the far side. One possible scenario then is that large impacts on the near side may have made it easier for lava to flow onto the surface. The moon is a very slightly scalene ellipsoid due to tidal stretching, with its long axis displaced 30 degrees from facing the Earth due to gravitational anomalies from impact basins. Its shape is more elongated than current tidal forces can account for. This fossil bulge indicates that the moon solidified when it orbited at half its current distance to the Earth, and that it is now too cold for its shape to restore hydrostatic equilibrium at its current orbital distance. The moon is by size and mass the fifth largest natural satellite of the solar system, categorizable as one of its planetary mass moons, making it a satellite planet under the geophysical definitions of the term. It is smaller than Mercury and considerably larger than the largest dwarf planet of the solar system, Pluto. The moon is the largest natural satellite in the solar system relative to its primary planet. The moon's diameter is about 3,500 kilometers more than 1/4 of Earth's, with the face of the moon comparable to the width of either mainland Australia, Europe, or the contiguous United States. The whole surface area of the moon is about 38 million square kilometers, comparable to that of the Americas. The moon's mass is 181 of Earth's, being the second densest among the planetary moons, and having the second highest surface gravity, after Io at 0.1654 g, and an escape velocity of 2.38 km, 8,600 km/h, 5,300 mph. The moon is a differentiated body that was initially in hydrostatic equilibrium, but has since departed from this condition. It has a geochemically distinct crust, mantle, and core. The moon has a solid iron-rich inner core with a radius possibly as small as 240 kilometers, 150 mm, and a fluid outer core primarily made of liquid iron with a radius of roughly 300 kilometers, 190 mm. Around the core is a partially molten boundary layer with a radius of about 500 kilometers, 320 mi. This structure is thought to have developed through the fractional crystallization of a global magma ocean shortly after the moon's formation, 4.5 billion years ago. Crystallization of this magma ocean would have created a mafic mantle from the precipitation and sinking of the minerals olivine, clinopyroxene, and orthopyroxene. After about 3/4 of the magma ocean had crystallized, lower density plagioclase minerals could form and float into a crust atop. The final liquids to crystallize would have been initially sandwiched between the crust and mantle, with a high abundance of incompatible and heat-producing elements. Consistent with this perspective, geochemical mapping made from orbit suggests a crust of mostly anorthosite. The moon rock samples of the flood lavas that erupted onto the surface from partial melting in the mantle confirm the mafic mantle composition, which is more iron-rich than that of Earth. The crust is on average about 50 kilometers, 31 meters thick. The moon is the second densest satellite in the solar system, after Io. However, the inner core of the moon is small, with a radius of about 50 kilometers, 220 mi or less, around 20% of the radius of the moon. Its composition is not well understood, but is probably metallic iron alloyed with a small amount of sulfur and nickel. Analyses of the moon's time-variable rotation suggest that it is at least partly molten. The pressure at the lunar core is estimated to be 5 GPa, $49,000 ATM. On average, the moon's surface gravity is 1.622 WASMS2, 0.16584 g, 5,318 FTOS2, about half of the surface gravity of Mars, and about a sixth of Earth's. The moon's gravitational field is not uniform. The details of the gravitational field have been measured through tracking the Doppler shift of radio signals emitted by orbiting spacecraft. The main lunar gravity features are mascons, large positive gravitational anomalies associated with some of the giant impact basins, partly caused by the dense mare basaltic lava flows that fill those basins. The anomalies greatly influence the orbit of spacecraft about the moon. There are some puzzles. Lava flows by themselves cannot explain all of the gravitational signature and some mascons exist that are not linked to mere volcanism. The Moon has an external magnetic field of less than 0.2 nanoteslas, or less than 100,000th that of Earth. The Moon does not have a global dipolar magnetic field and only has crustal magnetization, likely acquired early in its history when a dynamo was still operating. Early in its history, 4 billion years ago, its magnetic field strength was likely close to that of Earth today. This early dynamo field apparently expired by about 1 billion years ago, after the lunar core had crystallized. Theoretically, some of the remnant magnetization may originate from transient magnetic fields generated during large impacts through the expansion of plasma clouds. These clouds are generated during large impacts in an ambient magnetic field. This is supported by the location of the largest crustal magnetization situated near the antipodes of the giant impact basins. The Moon has an atmosphere consisting of only an exosphere, which is so tenuous as to be nearly vacuum, with a total mass of less than 10 tons, 9.8 long tons, 11 short tons. The surface pressure of this small mass is around 3 x 10 to 15 atm, 0.3 npa. It varies with the lunar day. Its sources include outgassing and sputtering, a product of the bombardment of lunar soil by solar wind ions. Elements that have been detected include sodium and potassium, produced by sputtering, also found in the atmospheres of Mercury and Io, helium-4 and neon from the solar wind, and argon-40, radon-222, and polonium-210, outgassed after their creation by radioactive decay within the crust and mantle. The absence of such neutral species, atoms or molecules, as oxygen, nitrogen, carbon, hydrogen, and magnesium, which are present in the regolith, is not understood. Water vapor has been detected by Chandrayaan-1 and found to vary with latitude, with a maximum at 60-70 degrees. It is possibly generated from the sublimation of water ice in the regolith. These gases either return into the regolith because of the Moon's gravity or are lost to space, either through solar radiation pressure or, if they are ionized, by being swept away by the solar wind's magnetic field. Studies of Moon magma samples retrieved by the Apollo missions demonstrate that the Moon had once possessed a relatively thick atmosphere for a period of 70 million years, between 3 and 4 billion years ago. This atmosphere, sourced from gases ejected from lunar volcanic eruptions, was twice the thickness of that of present-day Mars. The ancient lunar atmosphere was eventually stripped away by solar winds and dissipated into space. A permanent moon. Dust cloud exists around the Moon, generated by small particles from comets. Estimates are 5 tons of comet particles strike the Moon's surface every 24 hours, resulting in the ejection of dust particles. The dust stays above the Moon approximately 10 minutes, taking 5 minutes to rise and 5 minutes to fall. On average, 120 kilograms of dust are present above the Moon, rising up to 100 kilometers above the surface. Dust counts made by Leidy's Lunar Dust Experiment, LDEX, found particle counts peaked during the Geminid, Quadrantid, Northern Taurid, and Omicron Centaurid meteor showers, when the Earth and Moon pass through comet debris. The lunar dust cloud is asymmetric, being denser near the boundary between the Moon's dayside and nightside. Ionizing radiation from cosmic rays, their resulting neutron radiation, and the Sun results in an average radiation level of 1.369 millisieverts per day during lunar daytime 14, which is about 2.6 times more than the level on the International Space Station, 5 to 10 times more than the level during a transatlantic flight, and 200 times more than the level on Earth's surface. For further comparison, radiation levels average about 1.84 millisieverts per day on a flight to Mars, and about 0.64 millisieverts per day on Mars itself, with some locations on Mars possibly having levels as low as 0.342 millisieverts per day. Solar radiation also electrically charges the highly abrasive lunar dust and makes it levitate. This effect contributes to the easy spread of the sticky, lung and gear-damaging lunar dust. The Moon's axial tilt with respect to the ecliptic is only 1.5427 degrees, much less than the 23.4040 of Earth. This small axial tilt means that the moon's solar illumination varies much less with season than Earth's, and it also allows for the existence of some peaks of eternal light at the moon's north pole, at the rim of the crater Peary. The lunar surface is exposed to drastic temperature differences ranging from 120 degrees Celsius to 171 degrees, depending on the solar irradiance. Because of the lack of atmosphere, temperatures of different areas vary particularly upon whether they are in sunlight or shadow, making topographical details play a decisive role on local surface temperatures. Parts of many craters, particularly the bottoms of many polar craters, are permanently shadowed. These craters of eternal darkness have extremely low temperatures. The Lunar Reconnaissance Orbiter measured the lowest summer temperatures in craters at the southern pole at 35 K. Dust 238. Degsi 397 degree and just 26 K, 247 degree, 413 degree, close to the winter solstice in the North Polar crater Hermit. This is the coldest temperature in the solar system ever measured by a spacecraft, colder even than the surface of Pluto. Blanketed. On top of the moon's crust is a highly comminuted, broken into ever smaller particles, and impact-gardened mostly gray surface layer called regolith, formed by impact processes. The finer regolith, the lunar soil of silicon dioxide glass, has a texture resembling snow and a scent resembling spent gunpowder. The regolith of older surfaces is generally thicker than for younger surfaces. It varies in thickness from 10-15 Ma 3349 ft in the highlands and 4-5 m 1316 ft in the Maria. Beneath the finely comminuted regolith layer is the megaregolith, a layer of highly fractured bedrock many kilometers thick. These extreme conditions are considered to make it unlikely for spacecraft to harbor bacterial spores at the moon for longer than just one lunar orbit. The topography of the moon has been measured with laser altimetry and stereo image analysis. Its most extensive topographic feature is the giant far-side South Pole Aitken Basin, some 2,240 kilometers, 390 meters in diameter, the largest crater on the moon, and the second largest confirmed impact crater in the solar system. At 13 kilometers, 8.1 meters deep, its floor is the lowest point on the surface of the moon, reaching 9.178 kilometers, 5.103 meters, at 70.368 degrees, 172.413 degrees in a crater within Antoniadi crater, the highest elevations of the moon's surface, with the so-called Selenian summit at 10.629 kilometers, 6.605 meters, are located directly to the northeast, 5.44 Malmdi, 158.65 miles from 6 degrees, which might have been thickened by the oblique formation impact of the South Pole Aitken Basin. Other large impact basins such as Imbrium, Serenitatis, Crisium, Smithy, and Orientale possess regionally low elevations and elevated rims. The far side of the lunar surface is on average about 1.9 kilometers, 1.2 meters, higher than that of the near side. The discovery of fault scarp cliffs suggests that the moon has shrunk by about 90 meters, 300 ft, within the past billion years. Similar shrinkage features exist on Mercury. Mare Frigoris, a basin near the North Pole long assumed to be geologically dead, has cracked and shifted. Since the moon does not have tectonic plates, its tectonic activity is slow, and cracks develop as it loses heat. Scientists have confirmed the presence of a cave on the moon near the Sea of Tranquility, not far from the 1969 Apollo 11 landing site. The cave, identified as an entry point to a collapsed lava tube, is roughly 45 meters wide and up to 80 meters long. This discovery marks the first confirmed entry point to a lunar cave. The analysis was based on photos taken in 2010 by NASA's Lunar Reconnaissance Orbiter. The cave's stable temperature of around 17 degrees Celsius could provide a hospitable environment for future astronauts, protecting them from extreme temperatures, solar radiation, and micrometeorites. However, challenges include accessibility and risks of avalanches and cave-ins. This discovery offers potential for future lunar bases or emergency shelters. The main features visible from Earth by the naked eye are dark and relatively featureless lunar plains called Maria, singular mare, Latin for seas, as they were once, believed to be filled with water, are vast solidified pools of ancient basaltic lava. Although similar to terrestrial basalts, lunar basalts have more iron and no minerals altered by water. The majority of these lava deposits erupted or flowed into the depressions associated with impact basins, though the Moon's largest expanse of basalt flooding, Oceanus Procellarum, does not correspond to an obvious impact basin. Different episodes of lava flow in Maria can often be recognized by variations in surface albedo and distinct flow margins. As the Maria formed, cooling and contraction of the basaltic lava created wrinkle ridges in some areas. These low, sinuous ridges can extend for hundreds of kilometers and often outline buried structures within the mare. Another result of Maria formation is the creation of concentric depressions along the edges, known as arcuate rills. These features occur as the mare basalts sink inward under their own weight, causing the edges to fracture and separate. In addition to the visible Maria, the Moon has mare deposits covered by ejecta from impacts, called cryptomares. These hidden mares are likely older than the exposed ones. Conversely, mare lava has obscured many impact melt sheets and pools. Impact melts are formed when intense shock pressures from collisions vaporize and melt zones around the impact site. Where still exposed, impact melt can be distinguished from mare lava by its distribution, albedo, and texture. Sinuous rills, found in and around Maria, are likely extinct lava channels or collapsed lava tubes. They typically originate from volcanic vents, meandering and sometimes branching as they progress. The largest examples, such as Schroeder's Valley and Rima Hadley, are significantly longer, wider, and deeper than terrestrial lava channels, sometimes featuring bends and sharp turns that, again, are uncommon on Earth. Mare volcanism has altered impact craters in various ways, including filling them to varying degrees and raising and fracturing their floors from uplift of mare material beneath their interiors. Examples of such craters include Taruntius and Gassendi. Some craters, such as Hyginus, are of wholly volcanic origin, forming as calderas or collapse pits. Such craters are relatively rare and tend to be smaller, typically a few kilometers wide, shallower and more irregularly shaped than impact craters. They also lack the upturned rims characteristic of impact craters. Several geologic provinces containing shield volcanoes and volcanic domes are found within the near-side Maria. There are also some regions of pyroclastic deposits, scoria cones, and non-basaltic domes made of particularly high viscosity lava. Almost all Maria are on the near side of the Moon and cover 31% of the surface of the near side, compared with 2% of the far side. This is likely due to a concentration of heat-producing elements under the crust on the near side, which would have caused the underlying mantle to heat up, partially melt, rise to the surface, and erupt. Most of the Moon's mare basalts erupted during the Imbrian period, 3.3–3.7 billion years ago, though some being as young as 1.2 billion years and as old as 4.2 billion years. In 2006, a study of Ina, a tiny depression in Lacus Felicitatis, found jagged, relatively dust-free features that, because of the lack of erosion by infalling debris, appeared to be only 2 million years old. Moonquakes and releases of gas indicate continued lunar activity. Evidence of recent lunar volcanism has been identified at 70 irregular mare patches, some less than 50 million years old. This raises the possibility of a much warmer lunar mantle than previously believed, at least on the near side, where the deep crust is substantially warmer because of the greater concentration of radioactive elements. Evidence has been found for two 10 million years old basaltic volcanism within the crater Lowell, inside the Oriental Basin. Some combination of an initially hotter mantle and local enrichment of heat-producing elements in the mantle could be responsible for prolonged activities on the far side in the Oriental Basin. The lighter-colored regions of the Moon are called terrae, or more commonly highlands, because they are higher than most Maria. They have been radiometrically dated to having formed 4.4 billion years ago and may represent plagioclase cumulates of the lunar magma ocean. In contrast to Earth, no major lunar mountains are believed to have formed as a result of tectonic events. The concentration of Maria on the near side likely reflects the substantially thicker crust of the highlands of the far side, which may have formed in a slow-velocity impact of a second moon of Earth, a few tens of millions of years after the moon's formation. Alternatively, it may be a consequence of asymmetrical tidal heating when the moon was much closer to the Earth.